Welcome all. In the last sessions, we discussed about fixed axis rotation, that is pure rotation. In this session, we are going to discuss motion involving both translation and rotation. Now we are familiar with translation and also familiar with rotation motion. Now let us look how to address a motion which involves both translation and rotation. Now how we can explain a motion which involves both translation and rotation. That's what we are going to discuss here. You just look at some examples involving both translation and rotation. In the first image you can see a car, a running car. You just look at its tires. When the car is moving, its tires are rotating, at the same time it is translating also. Now the tires of a running car or tires of a running vehicle includes both translation and rotation. You can see a second image. The second image shows an inclined plane. You can see a spherical body on the inclined plane. We know what happens when you place a spherical body on the inclined plane. When you place a spherical body on a rough inclined plane, what happens is it will roll down. When the spherical body rolls down the inclined plane, you can see that this motion includes both translation and rotation. Both translation and rotation. At the same time, it is rotating. Also, it is translating from one place to other. So, and you can see a third example. Earth revolving around the sun. At the same time, Earth is spinning about its axis also. It also includes both translation and rotation. So now we are going to discuss the dynamics of such kind of motions which includes both translation and rotation. And you can see these three examples: a body rolling on a surface, a body rolling down inclined plane, and Earth or any other planet revolving around the sun. All are examples of such kind of motions. What we are going to do is we are going to discuss the dynamics of such kind of motions. We are familiar with rotational motion and also familiar with the translation motion. When this kind of motion comes, that is a motion which includes both translation and rotation, let us look how to address this motion. The motion involving both translation and rotation can be viewed as the combination of two motions. One is a translation of the center of mass of the body and rotation about the center of mass. We are familiar with translational motion and rotational motion. What actually we are doing here is we are converting a translational rotational motion into a translation and rotation. That is a translation of the center of mass plus rotation about the center of mass. To discuss the motion and to discuss the dynamics, we have to discuss about angular momentum of the body, torque and kinetic energy. These three parameters we will discuss here. Now let us first look what is the angular momentum of body in motion involving both translation and rotation. Again we can say that angular momentum of the body about the origin. Do remember that the angular momentum of a body is not unique. It depends upon the chosen origin. Now, while talking about angular momentum, we have to be very careful about which point we are talking about. So, the angular momentum of the body about the origin of an inertial coordinate system is the sum of angular momentum due to rotation of the body about its center of mass and the angular momentum due to motion of center of mass with respect to origin of the inertial coordinate system. This is what we have already discussed, that is the motion involving both translation and rotation can be viewed as the combination of translation of center of mass and rotation of center of mass. Now the angular momentum also we can divide into angular momentum due to rotation of body about its center of mass. You imagine that the body is rotating about the center of mass. Now calculate its angular momentum. And second is the angular momentum due to motion of center of mass with respect to origin of the inertial coordinate system. Now we are choosing a coordinate system. You calculate the angular momentum of the center of mass with respect to origin of the inertial coordinate system. This we will prove first. So let us look what does it mean. You just have a look. You consider a body. For the sake of simplicity, I am assuming a two-dimensional body, say like a body like disc. This is a center. It is actually rolling. Rolling is a combined translation rotation motion. The center of mass is moving with a velocity v. The velocity of center of mass is v. Velocity of center of mass is v. You can see here the velocity of center of mass. Let me put as capital V. V is the velocity of center of mass. The body is moving here. V is the velocity of center of mass. V is the velocity of center of mass. Now we can fix a coordinate system to talk about angular momentum. We do require a coordinate system. Let us draw some axis here. You just see this axis. Say this is x-axis. Let us draw y-axis. This is y-axis, and definitely you can see this is z-axis. X, Y, and Z axis you can see. This body is rolling. Body is rolling. That is, it have both the translation and rotation motion, and you can see that the axis of rotation is parallel to Z axis. Axis of rotation is the axis passing through the center of mass. Axis of rotation is the axis passing through the center of mass. Definitely that axis is parallel to Z axis, parallel to Z axis. Now the angular momentum of the body will be along Z direction. Now you can see the origin. You just see what is our statement. The angular momentum of the body about the origin of an inertial coordinate system. This is the origin. You can see the origin here. Origin of the inertial coordinate system. Origin of the inertial coordinate system. You can see origin here. Angular momentum about this origin is the sum of angular momentum due to rotation of the body about its center of mass. You just see this body is rotating about center of mass. Say I0 is the moment of inertia about center of mass, and omega is the angular velocity. Omega is the angular velocity. Now you can see angular momentum. Angular momentum due to rotation about center of mass. L due to rotation about center of mass equal to I0 omega. I0 omega. Angular momentum due to rotation of center of mass equal to I0 omega. Angular momentum due to rotation of center of mass is I0 omega. Now the angular momentum due to motion of center of mass with respect to origin of the inertial coordinate system. That is, you just see what is the angular momentum. Let us draw the position vector of center of mass. Say this is a position vector of center of mass. Say capital R is a position vector of center of mass. Position vector of center of mass. Capital V is the velocity. M is the mass of the body. Now angular momentum. Now what we have to calculate is angular momentum due to motion of center of mass. Due to motion of center of mass with respect to the point O. With respect to O equal to angular momentum due to motion of center of mass with respect to point O. You can see point O here. Now we know it is R cross P, R or R cross MV, R cross MV, R cross MV, and this will be in Z direction. So indicate that we can write it as Z direction, R cross MV. That will be in Z direction. This I0 omega also will be in Z direction, R cross MV in Z direction. Now we can say that this angular momentum that we denote by LZ. LZ equal to the angular momentum LZ equal to LZ simply means that the angular momentum will be along Z direction because axis of rotation is along Z direction. And one more thing, do remember that here we assume that the axis of rotation will not change. The direction of axis of rotation remains at Z axis. There are cases where the axis changes due to rotation, but here we are not taking such cases. In this situation, we are taking fixed axis. That is, the axis is translating only, axis is not rotating. That is why we have taken the angular momentum along Z axis. You can write Lz equal to I0 omega I0 omega plus R cross MV. You can write like this I0 omega plus R cross MV. This will be in Z direction. I0 omega plus R cross MV in Z direction. This is a mathematical form of the previous statement. You can see what is the statement. The angular momentum of the body about the origin of an inertial coordinate system is the sum of angular momentum due to rotation of the body about its center of mass. We wrote it as I0 omega and angular momentum due to motion of center of mass with respect to origin of the inertial coordinate system. This is R cross MV. R cross MV. R cross MV will be along Z direction, that we know. So what we are going to do is we are going to prove this. We are going to prove this statement. We are going to prove this statement. For that purpose, let us consider a rotating body as considered in the previous session. You consider a body which is rotating. We just consider this body. It is rotating. This is center of mass. Let us consider the axis. Let us consider the axis. So this is x-axis. For the sake of simplicity, I have taken body is lying in the xy plane. Body is lying in the xy plane. Say this is y-axis, and you can see this is z-axis, and the axis of rotation is z. Axis of rotation is z here. Now what to do is let us draw vectors. Just see the position vector of center of mass. This is position vector of center of mass. Let us put as capital R is the position vector of center of mass. Position vector of center of mass. Now, how to calculate the angular momentum? Now we know that the angular momentum of a body about any point is L equal to, we are familiar, L equal to summation over I Ri cross Pi. Summation over I Ri cross Pi. This is the angular momentum. Pi is Ri dot. You can write this as L equal to Ri cross Pi. Ri cross Pi. Now you consider a mass element here. Say this is Mi. This Mi has a position vector. You just see the position vector of Mi. Say this is Ri with respect to origin. With respect to origin, so that the angular momentum will be summation over I Ri cross Pi. That's a basic definition of angular momentum. Summation over I Ri cross Pi is the basic definition of angular momentum. Now you look center of mass. This mass is Mi. Now you consider a coordinate system with center of mass as origin. Say the position vector of this mass Mi will be Ri prime or Ri dash. Ri dash. Now from the triangle Ri and Ri prime, you can see that Ri equal to R plus Ri prime. Ri equal to R plus Ri prime we can write. Now L equal to Ri plus Pi. L can be written as you just see how we can write L. L can be written as summation over I Ri cross Pi is Mi Ri dot Mi Ri dot. Now Ri equal to R plus Ri prime. Now you have Ri dot equal to R dot plus Ri prime dot. Now let us substitute here. This is vector L, the angular momentum about the origin O. Now let us substitute for Ri. You have L equal to summation over I. Let's take Mi first. In place of Ri, R plus Ri prime. Then there is cross Ri dot. This is this cross R dot plus Ri prime dot. Let's evaluate this. The first term summation over I Mi R cross R dot. Second term plus summation Mi is R cross Ri prime dot Mi R cross Ri prime dot plus third term summation over I Mi Ri prime Mi Ri prime cross R dot plus fourth term summation over I Mi Ri prime cross Ri prime dot. These are the values. We know that R dot is V. We can write like this is equal to R cross R dot is capital V, velocity of center of mass. Velocity of center of mass. Summation over Mi is M. You can write the first term as, if record, you can take R outside, R cross summation over Mi into V, Mi into V plus, you can take R outside, R cross summation over Mi Ri prime dot plus summation over Mi Ri prime cross R dot plus summation over Mi Ri prime cross Ri prime dot. The value. You just see summation over Mi Ri prime is the sum of moments about center of mass. This is 0. You have this summation over Mi Ri prime equals 0. This is sum of moments about center of mass that we had already discussed. Since summation over Mi Ri prime equals 0, definitely summation over Mi Ri prime dot, its derivative will eventually vanish. So the second and third term will vanish, and finally we will arrive here L equal to, and also summation over Mi is total mass R cross MV, R cross MV plus summation over Mi Ri prime cross Ri prime dot. R cross MV plus summation over Mi Ri prime cross Ri prime dot. Now let us write it here. L equal to R cross MV plus summation over Mi Ri prime cross Ri prime dot. This is the angular momentum. This is the most general expression. It can be evaluated in various ways. Now here we are taking fixed axis only, that is the direction of axis is not changing. Now I am taking angular momentum along z direction. Now we had taken a special case only a special case is taken. Special case is taken, that is the angular momentum direction does not change during the motion. Say if you take Lz, angular momentum along z direction, you can write Lz equal to R cross MV in the z direction plus summation over Mi Ri dash cross Ri prime dot. This way we can write. It's set component. We have to take set component. Set component. Now we can evaluate the first term. We know that R cross MV is nothing but the angular momentum of center of mass about origin. First term is angular momentum of center of mass about origin, and second term let us evaluate. You just look this term, the second term, summation over mi ri prime cross ri prime dot, this can be written as summation over I mi ri prime cross this ri prime dot can be written as omega ri prime, omega ri prime. This will be equal to omega into summation over I mi ri prime square. Summation mi ri prime square is I0, and you can see that this is I0 omega. This is I0 omega. Now LZ become, you can see this LZ equal to I0 omega plus I0 omega plus R cross MV, R cross MV in Z direction, R cross MV in Z direction. This is what we have already stated and we proved it. Now let me summarize it. നമ്മൾ ഡിസ്കസ് ചെയ്തത് ട്രാൻസ്ലേഷനും റൊട്ടേഷനും ഒരുമിച്ച് വരുന്ന ഒരു ബോഡിയുടെ മോഷനാണ്. ഈ സിറ്റുവേഷനിൽ ബോഡിയുടെ ആംഗുലാർ മൊമെന്റം, ഞാൻ നേരത്തെ പറഞ്ഞിട്ടുണ്ട്, ഒരു ബോഡിയുടെ ആംഗുലാർ മൊമെന്റം എന്ന് പറയുന്നത് എല്ലായ്പ്പോഴും ഒരു പർട്ടിക്കുലർ ഒറിജിനെ അനുസരിച്ചായിരിക്കും, അത് യുണീക്ക് അല്ല. ഇപ്പൊ നമ്മളൊരു ഇനേഷ്യൽ കോർഡിനേറ്റ് സിസ്റ്റം എടുത്തു. ആ ഇനേഷ്യൽ കോർഡിനേറ്റ് സിസ്റ്റത്തിന്റെ ഒറിജിൻ എബൌട്ട് ആയിട്ടുള്ള ഈ ബോഡിയുടെ ആംഗുലാർ മൊമെന്റം എന്ന് പറയുന്നത് അതിനെ രണ്ട് ടേംസിന്റെ സം ആയിട്ട് എഴുതാൻ പറ്റും എന്ന് പറഞ്ഞു. ഒന്ന് ആംഗുലാർ മൊമെന്റം ഡ്യൂ ടു റൊട്ടേഷൻ അബൌട്ട് സെന്റർ ഓഫ് മാസ്, സെന്റർ ഓഫ് മാസിന് അബൌട്ട് ആയിട്ട് ഈ ബോഡി റൊട്ടേറ്റ് ചെയ്യുന്നതിന്റെ ആംഗുലാർ മൊമെന്റവും. രണ്ട് സെന്റർ ഓഫ് മാസ് മൂവ് ചെയ്യുന്നതിന്റെ, ഇനേഷ്യൽ കോർഡിനേറ്റ് സിസ്റ്റത്തിനെ റെസ്പെക്ട് ചെയ്തുകൊണ്ട് സെന്റർ ഓഫ് മാസിന്റെ മോഷൻ ഒരു ആംഗുലാർ മൊമെന്റ് ഉണ്ടാകും. ആ രണ്ടിന്റെയും സം ആയി എഴുതാമെന്നാണ് പറഞ്ഞത്. അതിനുശേഷം ആ റിലേഷൻ എഴുതി അതിനെ നമ്മൾ പ്രൂവ് ചെയ്തു. ഇതാണ് നമ്മൾ ഇപ്പോൾ ചെയ്തിരിക്കുന്നത്. എൽ സെറ്റ് എന്ന് പറയുന്നത് I0 ഒമേഗ പ്ലസ് ആർ ക്രോസ് എം വി എന്ന് നമ്മൾ പ്രൂവ് ചെയ്തിരിക്കുന്നു. ഇതുവരെ നമ്മൾ ഒരു ബോഡി റോൾ ചെയ്യുമ്പോൾ അതിന്റെ ആംഗുലാർ മൊമെന്റം ആണ് ഡിസ്കസ് ചെയ്തത്. അപ്പൊ നമ്മൾ കണ്ടു ഈ കമ്പൈൻഡ് ട്രാൻസ്ലേഷൻ റൊട്ടേഷൻ മോഷനിലെ ആംഗുലാർ മൊമെന്റം എന്ന് പറയുന്നത് ആംഗുലാർ മൊമെന്റം ഓഫ് റൊട്ടേഷൻ ഓഫ് സെന്റർ ഓഫ് മാസ് പ്ലസ് ആംഗുലാർ മൊമെന്റം ഓഫ് ട്രാൻസ്ലേഷൻ ഓഫ് സെന്റർ ഓഫ് മാസ് അബൌട്ട് ഒറിജിൻ ആണ് എന്ന് നമ്മൾ കണ്ടു. ഇനി നമ്മൾ ഒരു ഫെമിലിയർ എക്സാമ്പിൾ, നമ്മൾ നേരത്തെ മൂന്നാമത് പറഞ്ഞ എക്സാമ്പിൾ റവല്യൂഷൻ ഓഫ് എർത്ത് അറൌണ്ട് സൺ, അതിന്റെ സെൽഫ് റൊട്ടേഷൻ കൂടെ, ആ ഒരു എക്സാമ്പിൾ നോക്കുക. അതും ഈ ഒരു മോഷൻ എക്സാമ്പിൾ ആണ്. ട്രാൻസ്ലേഷൻ മോഷനും റൊട്ടേഷൻ മോഷനും ഒരുമിച്ച് വരുന്ന സിറ്റുവേഷൻ എക്സാമ്പിൾ ആണ്. ലെറ്റ് us look that situation. You can see the motion of earth around the sun here. The sun is here, you can see sun here, and this is earth. This earth, it has two motion. One, the motion of earth around the sun we call as the orbital motion, and another is the self rotation, is called spin motion. Both produces angular momentum. Now we can calculate what is the angular momentum of earth with respect to sun. To calculate angular momentum, it has two terms. One, the angular momentum due to self rotation, and the angular momentum due to orbital motion. And the first one we call as the spin angular momentum, and the angular momentum due to orbital motion is called orbital angular momentum. And you know, the daily rotation of earth about its axis give rise to that spin angular momentum. Self rotation ആണ് spin angular momentum ഉണ്ടാക്കുന്നത്. The annual revolution of earth about the sun give rise to that's orbital angular momentum about sun, orbital angular momentum. And the total angular momentum will be definitely the sum of the spin angular momentum and ഓർബിറ്റൽ ആംഗുലാർ മൊമെന്റം. ഇതിന്റെ ടോട്ടൽ ആംഗുലാർ മൊമെന്റം എന്ന് പറയുന്നത് സ്പിൻ ആംഗുലാർ മൊമെന്റം, അതായത് ഡെയിലി റൊട്ടേഷൻ കൊണ്ടുണ്ടാവുന്ന ആംഗുലാർ മൊമെന്റത്തിന്റെയും ആനുവൽ റവല്യൂഷൻ കൊണ്ടുണ്ടാവുന്ന ആംഗുലാർ മൊമെന്റത്തിന്റെയും സം ആയിരിക്കും. നോക്കൂ, സ്പിൻ ആംഗുലാർ മൊമെന്റം intrinsic ആണ്. Spin angular momentum is intrinsic to the body, that is no change in coordinate system can eliminate spin. If you take coordinate system anywhere, the spin angular momentum will be unique because it is the angular momentum with respect to rotation about the center of mass. That is, spin angular momentum is intrinsic to the body, no change in coordinate system can eliminate spin. And the orbital angular momentum disappears. That is, the orbital angular momentum depends on the choice of origin. So if you take origin somewhere, the orbital angular momentum will be different, and the orbital angular momentum disappears if the origin is along the line of motion. The orbital angular momentum disappears if the origin is along line of motion. ഇപ്പൊ നമ്മൾ ആംഗുലാർ മൊമെന്റം ആണ് ഡിസ്കസ് ചെയ്തത്. ഇനി നമുക്ക് ഡിസ്കസ് ചെയ്യേണ്ടത് ടോർക്കും കൈനറ്റിക് എനർജിയുമാണ്. ഈ രണ്ട് ടേംസ്, അതായത് റൊട്ടേഷൻ ഡൈനാമിക്സ് ഡിസ്കസ് ചെയ്യുമ്പോഴേക്കും നമുക്ക് ഏറ്റവും പ്രധാനപ്പെട്ട മൂന്ന് കാര്യങ്ങൾ, ഒന്ന് ബോഡിയുടെ ആംഗുലാർ മൊമെന്റം എന്തായിരിക്കും, അതുപോലെ ബോഡിയുടെ മുകളിൽ ആക്ട് ചെയ്യുന്ന ടോർക്ക് എന്തായിരിക്കും, അതുപോലെ ബോഡിയുടെ കൈനറ്റിക് എനർജി എന്തായിരിക്കും. ഇത് നമ്മൾ ഡിസ്കസ് ചെയ്യാൻ പോകുന്നത് ഈ കമ്പൈൻ ട്രാൻസ്ലേഷൻ റൊട്ടേഷൻ മോഷനിലെ ടോർക്കും കൈനറ്റിക് എനർജിയും എന്തായിരിക്കും എന്നാണ്. നോക്കൂ, ടോർക്ക് ഓൺ ബോഡി ഇൻ മോഷൻ ഇൻവോൾവിംഗ് ബോത്ത് ട്രാൻസ്ലേഷൻ റൊട്ടേഷൻ. ലെറ്റ്സ് ലുക്ക് ഹൗ വി അഡ്രസ് ടോർക്ക്. We know kinetic energy equal to, we can write, torque equal to summation over I Ri cross Fi. This torque. Torque equal to summation over I Ri cross Fi. That is, suppose you have this coordinate system. The body is moving. You take a particle, say the force acting on it is Fi, and its position vector is, say the position vector is Ri. The total torque will be summation over I Ri cross Fi. This is a torque, summation over I Ri cross Fi. As in the previous case, we can write summation over I. Ri is Ri dash plus R. Ri dash plus R cross Fi. This can be written as summation over I Ri dash cross Fi plus R cross summation over I Fi. You can write this as summation over I Ri dash cross Fi, Ri dash cross Fi plus R cross F, net external force, R cross F. Now if you take a fixed axis, you can write Ri dash cross Fi. You can just write tau Z. If you assume that the direction of axis is not changing, tau Z equal to summation over I Ri dash cross Fi Z direction plus R cross F in Z direction. R cross F in Z direction, we can write so, R cross F in Z direction. Now you can see the two terms in equation. and the torque on the body about the origin of an inertial coordinate system is the sum of torque about center of mass due to various external forces and the torque due to total external force acting at the center of mass. You just see this equation. നമ്മളിപ്പോൾ ഓൾറെഡി എഴുതിയിരിക്കുന്ന ഇക്വേഷൻ ഉണ്ട്. എന്താ ഇക്വേഷൻ നോക്കുക. ടോ എന്നത് ടോ ഈക്വൽ ടു summation over I Ri prime cross Fi tau Z. If you take tau Z plus R cross F എന്ന് എഴുതാം. R cross F എന്ന് എഴുതാം. Say this also in Z direction. If you take fixed axis R cross F. ഇതിൽ ഓരോ ടേമും എന്താ നോക്കൂ. The first term is torque about center of mass due to വേരിയസ് എക്സ്റ്റേണൽ ഫോഴ്സ് ആണ്. അതായത് എഫ് ഐ എന്ന് പറയുന്ന വേരിയസ് എക്സ്റ്റേണൽ ഫോഴ്സ് കൊണ്ട് സെന്റർ ഓഫ് മാസിന് എബൌട്ട് ആയിട്ടുള്ള ടോർക്കാണ് ഇതിനകത്ത് ഫസ്റ്റ് ടേം. സമ്മേഷൻ ഓവർ ഐ ആർ ഐ പ്രൈം ക്രോസ് എഫ് ഐ എന്നത് ടോർക്ക് അബൌട്ട് സെന്റർ ഓഫ് മാസ് ഡ്യൂ ടു വേരിയസ് എക്സ്റ്റേണൽ ഫോഴ്സസ് ആണ്. ആൻഡ് സെക്കൻഡ് ടേം ആർ ക്രോസ് എഫ് എന്ന് പറയുന്നത് ടോർക്ക് ഡ്യൂ ടു ടോട്ടൽ എക്സ്റ്റേണൽ ഫോഴ്സ് ആക്ടിങ് അറ്റ് ദ സെന്റർ ഓഫ് മാസ് ആണ്. ഈ രണ്ട് ടേംസിന്റെ സം ആയി നമുക്ക് ടോർക്കിന് എഴുതാം. ഞാൻ ഇതിലെ ഫസ്റ്റ് ടേമിനെ ലെറ്റ് മീ ഡിനോട്ട് ബൈ tau 0. If you denote by tau 0 plus r cross f എന്ന് എക്സ്പ്രസ് ചെയ്യാൻ പറ്റും. tau 0 plus r cross f എന്ന് എക്സ്പ്രസ് ചെയ്യാൻ പറ്റും. ഇനി നമ്മൾ ആംഗുലാർ മൊമെന്റം ടോർക്ക് റിലേഷൻ ഒന്ന് ടോർക്ക് ഉണ്ടാക്കി നോക്കൂ. You have L Z. We already know this is I0 omega plus r cross mv. R cross mv in z direction. I0 omega plus r cross mv. I0 omega plus r cross mv. You take, we know that tau z equal to dlz by dt. You take derivative, this I0 d omega by dt plus d by dt of r cross mv. R cross mv. Now you can write d omega by dt is alpha. I0 alpha plus r cross m dv by dt. This I0 alpha plus r cross m dv by dt is acceleration of center of mass. M into acceleration of center of mass is total force. This I0 alpha plus r cross f. Definitely it will be in z direction. All belongs to z component in a fixed direction, r cross of z direction. Now if you compare with the previous equation, you can see that this tau 0, the angular momentum about center of mass is I0 alpha. I0 alpha. I0 alpha. Now you can write tau equal to I0 alpha plus I0 alpha plus r cross f in z direction. This is a torque about z axis for a rolling body. Now let us look the kinetic energy of a body in motion involving both translation and rotation. Kinetic energy. We know kinetic energy is equal to half summation over I mi vi square. That is half summation over I mi vi is ri dot square. Now half summation over I mi ri dot is ri prime dot plus v square, because you know this ri equal to ri prime plus r, then ri dot equal to ri prime dot plus r dot equal to v. That's what we have substituted here. Now you can write this as half summation over I mi ri prime dot square plus summation over I mi ri prime dot v plus half summation over I mi v square. Now we can write this as half summation over I mi ri prime dot is omega ri prime whole square plus summation over I mi ri prime dot v plus half summation over I mi is mv square. And do remember that summation over I mi ri prime, the sum of moments about center of mass is 0. Now the second term vanishes. Now you can write k equal to half summation over I mi ri prime square omega, and second term is plus half mv square. Summation over I mi ri prime square is half this I0, moment of inertia about center of mass, half I0, here omega square is here, omega square, half I0 omega square plus half mv square, half I0 omega square plus half mv square. This is the kinetic energy. And the kinetic energy, we can see there are two terms in kinetic energy. One is kinetic energy of spin, kinetic energy of rotation about center of mass, and kinetic energy of orbital motion of center of mass or orbital center of mass motion. You can see two terms here. The first term, this is the kinetic energy of rotation about center of mass. This is kinetic energy of rotation about center of mass. This is kinetic energy of translation of center of mass. That is one spin and other orbital motion. You can see the two terms in kinetic energy. One is the kinetic energy of spin and second is the kinetic energy of orbital center of mass motion. So ഈ സെഷനിൽ നമ്മൾ കമ്പൈൻഡ് ട്രാൻസ്ലേഷൻ റൊട്ടേഷൻ മോഷൻ വിധേയമാകുന്ന ഒരു ബോഡിയാണ് ഡിസ്കസ് ചെയ്തത്. അതിന്റെ ആംഗുലാർ മൊമെന്റം ഡിസ്കസ് ചെയ്തു, ടോർക്കും കൈനറ്റിക് എനർജിയും, ഈ മൂന്ന് കാര്യങ്ങളാണ് ഈ ടോപ്പിക്കിൽ ഡിസ്കസ് ചെയ്തത്. നമ്മൾ കണ്ടത് ആംഗുലാർ മൊമെന്റം എന്നത് രണ്ട് ടേംസിന്റെ സം ആയിരിക്കും. വൺ ആംഗുലാർ മൊമെന്റം ഓഫ് ബോഡി അബൌട്ട് സെന്റർ ഓഫ് മാസും സെക്കൻഡ് ആംഗുലാർ മൊമെന്റം ഓഫ് സെന്റർ ഓഫ് മാസ് അബൌട്ട് ഒറിജിനും ആയിരിക്കും. അതുപോലെ ടോർക്ക് ആയാൽ ടോർക്കിൽ നമ്മൾ കണ്ടത് ടോർക്കിലും രണ്ട് ടേം ഉണ്ട്. വൺ ടോർക്ക് ഓഫ് ബോഡി അബൌട്ട് സെന്റർ ഓഫ് മാസ്, സെക്കൻഡ് ടോർക്ക് ഓൺ സെന്റർ ഓഫ് മാസ് ഡ്യൂ ടു ഓൾ അപ്ലൈഡ് ഫോഴ്സസ്. ഈ രണ്ട് കാര്യങ്ങൾ കണ്ടു. കൈനറ്റിക് എനർജി വന്നപ്പോഴേക്കും നമ്മൾ കണ്ടത് അങ്ങനെയാണ്. കൈനറ്റിക് എനർജി രണ്ട് ടേംസ് ഉണ്ട്. വൺ ഈസ് ദ കൈനറ്റിക് എനർജി ഓഫ് സ്പിൻ ആൻഡ് സെക്കൻഡ് ഈസ് ദ കൈനറ്റിക് എനർജി ഓഫ് ഓർബിറ്റൽ മോഷൻ. അപ്പൊ നമ്മൾ മനസ്സിലാക്കിയത്, if you are dealing with a motion which involves both translation and rotation, you can deal the problem as two. One, the translation motion of center of mass, and two, the rotation of body about center of mass. ഈ രണ്ട് ഡൈനാമിക്സ് ആണ് നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത്. So thank you all for hearing this session. Thank you.